Welcome, curious minds, to the deep dive. It's pretty rare, isn't it, for just one name to leave such a massive mark on history?
It really is, especially a name that goes beyond just, one field.
Exactly. Today we're talking about a name that isn't just about science, though obviously it is. It's synonymous with, well, with human curiosity itself. About the universe.
You mean Albert Einstein?
Albert Einstein, visionary, philosopher, humanitarian icon. His name basically is our quest to understand the cosmos. He really shaped how we think in the modern age.
Absolutely. It's not just the equations, complicated as they are. It's how he fundamentally changed our view of reality. Time, space, matter.
Before him, time was like this fixed river, right? Just flowed the same for everyone.
Yeah, pretty much. But he showed us it's more like a current, and it flows differently depending on who's watching, where you are. It completely reshaped how we see existence itself.
Okay, so our mission here in this deep dive is to explore Einstein's life, which was pretty extraordinary. His revolutionary science, definitely.
And his philosophy too, right? His whole take on the universe.
Yes, exactly. His key works and the legacy he left behind, it's huge. We've gone through a lot of sources, and the goal is to pull out the most important bits, the key insights.
Kind of like a shortcut to getting up to speed on this incredible figure.
Exactly, a direct download into his world-changing ideas, hopefully.
And what's really cool is that his path to genius wasn't straightforward. Not at all.
Right, lots of surprising moments, even from when he was a kid.
Totally. Like that story about the compass. How that simple thing sparked this lifelong fascination with, the hidden forces in the universe.
Or that question he asked about riding alongside a beam of light. Seems almost childish, but
But it laid the groundwork for relativity. It's amazing. It really gets you thinking about how genius actually works.
it does. So it's going to be a fascinating journey, I think, into the mind of a true genius. How one person's curiosity could unravel so much. Ready to dive in?
Let's do it.
Okay, let's unpack this a bit. Albert Einstein, born March 14th, 1879. Ulm, Germany, Jewish family.
Right. His father, Hermann, was an electrical engineer, and his mother, Pauline, she was a musician. So a mix of technical and artistic influence, maybe.
Maybe. But when you think of someone who'd totally rewrite physics, you might expect, I don't know, obvious signs of brilliance from the start, right?
Yeah, a typical prodigy narrative. But the sources say his early years were, well, pretty ordinary on the surface. He wasn't dazzling everyone from the crib.
But there were hints, subtle things, like the late talking.
Right, that's a classic story.
Yeah.
His parents were apparently worried. But looking back, maybe it wasn't a deficit. Maybe it showed he was thinking deeply.
How so?
Well, some interpretations suggest he was forming complete thoughts, like fully internally before speaking them, processing the world very methodically, even as a toddler. It hints at that deep rumination he was known for later.
Interesting. And then came the compass moment, age 5.
Yeah, that's the pivotal one. His dad gives him the simple magnetic compass. And the needle, it just keeps pointing north. Always, no matter how you turn the compass.
Guided by some unseen force.
Exactly. And for young Einstein, that was mind-blowing. It wasn't just a toy, it was a mystery. A hint of some hidden order in the world. That little needle ignited this intense curiosity about the physical world's secrets.
And set him on that path of inquiry. It's amazing how a small thing.
It really is. That magnetic pole, totally invisible, started this lifelong quest to figure out the underlying rules of the universe.
But it wasn't all smooth sailing after the compass, was it? Schooling was tough for him.
Oh yeah, the German system back then was very rigid, very authoritarian, lots of rate memorization.
And he hated that, especially at the Luitpold Gymnasium in Münster.
He really did. It makes you think, what's it like for a mind that just wants to question everything, to explore, stuck in a system that demands conformity? Pure repetition.
Must have felt like a prison.
Pretty much. It was a fundamental clash. His whole nature was inquisitive, independent. He didn't want to just be told things. He wanted to figure them out himself from first principles.
So he found refuge elsewhere.
Definitely. In math and physics. That's where he could really let his mind roam free. He discovered Euclidean geometry around age 12.
And loved it.
Absolutely. He called it a love affair. Not just learning theorems, but seeing the logical beauty, the elegance of it, how you could build truths with pure reason. That appreciation for mathematical rigor became, like, his signature.
And then his family moved to Italy. He was about 16.
Yeah, his father's business wasn't doing well, so they moved, and he actually studied independently for a bit. And that freedom, away from the rigid schooling, That's when he asked that key
The
question.
light beam question.
What would happen if I ran alongside a light beam? Seems simple, maybe even silly, but it was a profound thought experiment.
How so?
Directly challenged Newtonian ideas about light and motion. It was him intuitively grappling with the concepts that would become special relativity years later, thinking about perspective, speed.
Just incredible, that one question. Okay, so after all that, he eventually gets into the Swiss Polytechnic Institute, ETH Zurich, now in 1896, for physics and math.
Right. Top school. But even there, not a perfect fit. He clashed with professors. Frequently.
Okay, let's unpack that. What does that tell us about him, his learning style, maybe his view of authority?
It tells us a lot.
Yeah.
He wasn't there to just soak up information like a sponge. He was a critical thinker. He questioned everything, challenged assumptions, even from respected professors.
Probably didn't make him popular with all of them.
Definitely not. Some wanted students who just, followed the script. But that independent questioning spirit, that's exactly what he needed to make his breakthroughs. He had to see beyond the accepted stuff.
And it was around this time he met Mileva Maric.
Yes, a fellow physics student from Serbia.
Oh.
Very bright. The sources suggest she was really important, not just personally, but intellectually. A peer he could really engage with on physics.
Shared that passion.
Exactly. But after graduating in 1900, finding a job was tough.
Really? With that mind?
Yeah, surprising, isn't it? His unconventional style, maybe some anti-Semitism. Getting an academic position was hard. So he ends up in 1902 at the Swiss Patent Office in Bern.
Reviewing patent applications seems mundane.
On the surface,
No.
maybe. But it was crucial. It gave him a steady income, which he needed. And maybe more importantly, it gave him time. Undisturbed time and mental space to just think about theoretical physics while looking over designs for, electrical devices and things.
So the routine work actually freed his mind.
He said so himself later.
Yeah.
He let his mind wander, build those thought experiments. It was like this quiet period of intense incubation before everything exploded.
And explode it did. Because just a few years later, 1905, from that very patent office, he's only 26.
Yeah, and he publishes 4 papers. 4.
Mhm.
Each one revolutionary. It completely changes physics.
We call it the Annus Mirabilis, the miracle year. It's almost unbelievable, that level of output from one person in 1 year.
It truly is unprecedented.
Yeah.
A scientific supernova. 4 papers, each tackling a different fundamental problem. Just staggering.
But it wasn't like everyone immediately went, wow, genius.
Oh, definitely not. Initially, there was a lot of skepticism, even disbelief. These ideas were so radical, so far outside the box. They challenged Newtonian physics, which had been the gold standard for centuries,
That's how did he handle that?
with incredible patience, actually, and conviction. He knew he was onto something, and crucially, he backed it all up with solid math, impeccable logic. These weren't just wild guesses. They were carefully constructed theories with testable predictions.
Okay, let's break down those 4 papers. First up, the photoelectric effect. This is where it gets really interesting, challenging how people thought about light itself.
Right. For ages, light was understood mainly as a wave. Think ripples on water. That explained a lot, like diffraction. But it couldn't explain the photoelectric effect properly.
Which is?
Basically, when light hits a metal surface, sometimes it knocks electrons loose. But the wave theory couldn't explain why it only happened if the light had a certain minimum frequency, no matter how bright the light was, or why the electrons popped out instantly.
So what was Einstein's radical idea?
He took Max Planck's earlier idea about energy coming in packets, or quanta, and applied it to light itself. He proposed that light isn't just a continuous wave, but it also travels in these discrete little bundles of energy.
Which he called quanta, later known as photons.
Exactly. Photons. Little particles of light energy. This idea perfectly explained all the weirdness of the photoelectric effect. The energy of the photon depended on frequency, not intensity. That's why only certain frequencies could knock electrons out.
And this wasn't just some theoretical quirk, it was huge.
Monumental. It laid the foundation for quantum mechanics, which is, one of the 2 pillars of modern physics alongside relativity. And this is the work that actually won him the Nobel Prize in 1921.
Not relativity, that surprises people.
Yeah, relativity was still maybe a bit too controversial then. But the photoelectric effect had clear experimental backing and huge implications. And think about it today.
Solar panels.
Solar panels work because of this. Digital cameras, the sensors in your phone, all rely on light behaving like particles to generate electrical signals. It's amazing how that abstract idea from 1905 is literally in your pocket right now.
Mind-boggling. Okay, paper number 2 from the miracle year. Brownian motion. Sounds a bit obscure. The random jiggling of tiny particles in water.
It does sound obscure, like pollen grains dancing around randomly in water under a microscope,
Yeah.
but its significance was massive.
Why? What was the big deal?
At the time, believe it or not, the actual physical existence of atoms was still debated by some serious scientists. They were seen more as a useful concept, maybe, but not necessarily real things.
So Einstein tackled this jiggling.
Yeah, he used math, incredible mathematical modeling, to show that this random movement was direct evidence of something unseen. It was the result of the microscopic visible particles being constantly bombarded by even smaller invisible atoms and molecules in the fluid.
Like tiny billiard balls hitting the pollen.
Exactly. And he didn't just say that. He provided precise mathematical predictions about how those particles should move, how far they travel on average, predictions that could be tested experimentally.
And they were confirmed.
They were. And this provided really strong, quantifiable proof for the reality of atoms and molecules. It wasn't just a theory anymore.
So it bridged chemistry and physics.
Absolutely. It solidified the atomic theory of matter, gave it a firm physical footing, moved atoms from being just a useful idea to being, undeniably real, changed everything at the fundamental level of what matter is.
Okay, on to number 3. Arguably the most famous one. The special theory of relativity. This changed everything about time and space. So, break it down for us. What's the core idea here?
Special relativity is built on two seemingly simple postulates, but they have huge consequences. First, the speed of light in a vacuum is constant. Always the same, about 186,282 miles per second, no matter how fast you're moving when you measure it.
Which is weird, right? Usually speeds that up.
Totally weird. It defies common sense and classical physics. Second postulate, the laws of physics are the same for everyone who isn't accelerating. So, same rules apply, whether you're standing still or moving smoothly in a straight line.
Okay. Simple starting points, but they lead where?
They lead to mind-bending conclusions. Like time and space aren't absolute fixed backgrounds like Newton thought. They are relative. They depend on the observer's motion. Meaning things like time dilation, time actually passes slower for objects moving very fast compared to stationary ones. And length contraction objects appear shorter in the direction they're moving at high speeds. These aren't illusions, they're real physical effects.
Wow. And then the big one, EMC happy way.
Ah, yes. The world's most famous equation. It pops out as a consequence of special relativity. It's this profound statement that mass m and energy E are basically the same thing, just different forms, and they can be converted into each other, linked by the speed of light squared, c Gaia, which is a huge number.
So tiny mass equals huge energy.
Exactly. A minuscule amount of mass contains an absolutely enormous amount of locked-up energy. Think about it. C squared is just a massive conversion factor. This equation revealed the source of energy in radioactive decay in stars.
And unfortunately, the potential for nuclear weapons.
Yes. While Einstein wasn't involved in building the bomb, his equation provided the fundamental theoretical understanding of how much energy could be released by converting mass. It unlocked the secret that matter itself is concentrated energy.
Incredible. So that equation wasn't just a formula. It was a key to understanding the universe's engine room.
Precisely. It connected mass and energy in a way no one had conceived before. It unified these concepts, showing matter is frozen energy, energy can become matter. It gave a whole new perspective on everything from particle physics to how stars shine. It underpins so much of modern physics.
Okay, so if special relativity dealt with constant motion, Einstein wasn't done. He then spent years tackling acceleration and gravity, leading to his masterpiece, The General Theory of Relativity, published in 1915.
Right. If special relativity was revolutionary, general relativity was. Well, it was on another level entirely. It wasn't just tweaking Newton's gravity, it was a completely new way of thinking about it.
Newton saw gravity as a force, right? An invisible pull between objects, like the apple falling.
Exactly. Action at a distance. Einstein said, no, that's not quite right. Gravity isn't a force pulling things across space. Gravity is the shape of space-time itself.
The shape of space-time, how does that work?
Okay, think of space-time, the three dimensions of space plus time, as like a flexible fabric, a rubber sheet. Now put something heavy on it, like a bowling ball representing the sun. What happens?
It creates a dip, a curve in the sheet.
Exactly. It warps the fabric. Now, roll smaller marbles, like planets nearby. They don't get pulled by the bowling ball directly. They just follow the curves, the dips in the rubber sheet created by the bowling ball.
So planets orbit the sun because they're following the curve in space-time the sun creates.
Precisely. They're just moving along the straightest possible path, the geodesic, through that curved space-time. Gravity is geometry. It's the geometry of space-time being shaped by mass and energy.
That's a radical idea. And mathematically complex, I assume?
Oh, incredibly complex.
Yeah.
It required mastering really advanced mathematics, differential geometry, tensor calculus, stuff needed to describe curved spaces. It took him nearly a decade after special relativity to fully work it out.
And one of the craziest predictions was that even light, which has no mass, should follow these curves. Its path should bend near massive objects.
Yes, because light travels through space-time, and if space-time itself is curved, light's path must curve too. This was a stunning prediction, totally different from Newton's theory.
And this led to that famous experiment during the solar eclipse.
The crucial test. In 1919, the British astronomer Arthur Eddington led expeditions to photograph stars near the sun during a total solar eclipse. The sun's massive gravity should bend the starlight coming from behind it, making the stars appear slightly shifted in position.
And did it?
It did. And by exactly the amount Einstein's general relativity predicted, which was twice the deflection expected under older theories. The measurements confirmed it. Eddington's results were wired around the world.
Making Einstein a global superstar overnight?
Pretty much. Newspapers everywhere ran huge headlines. Lights all askew in the heavens, revolution in science, new theory of the universe, Newton overthrown. It was this massive public validation. Suddenly, everyone knew his name.
It's amazing. And this theory, general relativity, over 100 years old now, it still impacts us today. It's not just for astrophysicists.
Not at all. It's fundamental to modern cosmology. It's the basis for understanding black holes, where space-time is curved so extremely that nothing escapes. It underpins the Big Bang theory, the expansion of the universe.
But everyday stuff, too.
Absolutely, your GPS. The satellites orbiting Earth are in a weaker gravitational field than we are down here. General relativity predicts that time actually passes slightly faster for them because of that difference in gravity.
Seriously, time runs faster up there.
It's a tiny bit, but enough to matter. GPS systems have to constantly correct for this relativistic time difference. If they didn't account for Einstein's theory, the location errors would build up incredibly fast, like miles per day. Your phone's navigation wouldn't work.
Wow. So every time I use maps, I'm using general relativity. That's incredible. Okay, let's shift gears a bit. Einstein helped kickstart quantum theory with the photoelectric effect.
Yeah, he was a pioneer there.
But he famously wasn't comfortable with where quantum mechanics went,
Right.
especially the uncertainty, the probability stuff.
Right. That's one of the great ironies. He helped birth it, but he couldn't accept its fundamental weirdness, particularly the Copenhagen interpretation championed by Niels Bohr and Werner Heisenberg.
The idea that things are inherently fuzzy or probabilistic until measured.
Exactly. Einstein hated that. His famous line, "God does not play dice," sums it up perfectly.
Yeah.
He felt there had to be a deeper, deterministic reality underneath. Hidden variables, he thought. He believed quantum mechanics was incomplete.
So he argued about it a lot.
Oh, constantly. Legendary debates with Bohr, Schrödinger, Born. These were intellectual titans clashing over the very nature of reality. Bohr would argue that the quantum world is inherently probabilistic. Einstein just couldn't stomach it.
But his skepticism wasn't just negative.
Not at all. His persistent questions, his thought experiments challenging quantum mechanics, actually forced the proponents to sharpen their arguments, to explore the implications more deeply. His criticisms, in a way, made quantum theory stronger by testing it so rigorously. He was its most brilliant critic.
Okay, turning to a darker side, or at least a more complex one. Ep.2, the connection to the atomic bomb.
Yeah, that's the heavy part. It's the unavoidable implication of mass-energy equivalence.
Did Einstein work on the bomb itself, the Manhattan Project?
No, he wasn't directly involved. His background made him a security risk in the eyes of the U.S. government at the time, ironically. But his equation was the bedrock. It showed the possibility of releasing immense energy from matter.
And he wrote that letter to President Roosevelt in 1939.
Yes, urged by other physicists like Leo Szilard, they were terrified that Nazi Germany might be developing nuclear weapons. So Einstein, despite his pacifism, signed a letter urging the U.S. to accelerate its own research. It was a lesser of two evils kind of calculation.
But he regretted it later.
Deeply. After Hiroshima and Nagasaki, he was horrified by the destructive power unleashed. He became a passionate advocate for nuclear disarmament and international control of atomic energy. He co-founded the Emergency Committee of Atomic Scientists.
It really highlights the ethical burden on scientists, doesn't it, when pure knowledge leads to such devastating applications?
Absolutely. It's a dilemma that weighs heavily, or should weigh heavily, on scientific discovery. Einstein felt that weight profoundly.
Speaking of cosmic implications, back to general relativity. His own equations suggested the universe wasn't static, right? That it should be expanding or contracting.
Yes, that was the natural mathematical consequence. But the prevailing view back then was a static, eternal universe. It was almost philosophical dogma.
So Einstein adjusted his theory.
He did. He introduced something called the cosmological constant into his equations, basically a kind of hypothetical anti-gravity force to counteract gravity and keep the universe static, matching the accepted view.
But then Hubble came along.
Right. Edwin Hubble's observations in the late 1920s showed definitively that galaxies are moving away from us, and the farther they are, the faster they recede. The universe is expanding.
And Einstein's reaction.
He reportedly called the cosmological constant his biggest blunder. He realized he should have trusted his original equations, even if they contradicted the prevailing wisdom.
But there's a twist, right? That blunder isn't seen as such a blunder anymore.
Exactly. It's an amazing turnaround. In modern cosmology, something very much like Einstein's cosmological constant is back. It's now the leading explanation for dark energy.
The mysterious force causing the universe's expansion to accelerate.
Precisely. So his mistake turned out to be incredibly prescient, hinting at something profoundly important about the cosmos that we're only now beginning to understand. Even his blunders were brilliant.
That's incredible. So in his later years, after all this, he focused on one big, unfinished quest.
The unified field theory, his holy grail. He spent the last decades of his life trying to find a single mathematical framework, a theory of everything that could unite gravity, general relativity, with electromagnetism, and potentially the other forces too.
Combining the very large with the very small, basically.
That was the goal, to show that all the fundamental forces were just different aspects of one underlying reality. It was an incredibly ambitious goal.
Did he succeed?
No, he didn't achieve it in his lifetime. Reconciling general relativity, which describes smooth space-time, with quantum mechanics, which is inherently lumpy and probabilistic, is fiendishly difficult. Physicists are still working on it today.
But his pursuit still inspires them.
Absolutely. His relentless search continues to motivate fields like string theory, loop quantum gravity, all trying to crack that same fundamental problem. It shows his incredible foresight, identifying the deepest questions that would drive physics for the next century and beyond.
So beyond the scientist, let's talk about Einstein, the thinker, the humanist. His scientific work seems deeply connected to his philosophy, doesn't it?
Very much so.
Yeah.
It wasn't just about math for him. He had this pantheistic view, influenced a lot by the philosopher Spinoza. He didn't believe in a personal God who intervenes in our lives.
But he talked about God. God does not play dice.
Right, but for him, God was more like the inherent order, the harmony, the deep rationality and comprehensibility of the universe itself, the laws of nature. He found something deeply spiritual, a cosmic religious feeling in the beauty and elegance of those laws.
So understanding the universe was a kind of religious experience for him.
In a way, yes. A sense of awe and reverence for the intricate structure of reality. He believed the most incomprehensible thing was that the universe is comprehensible at all, that we can understand it through reason and science.
And his political and social views, they were quite strong too. Zionism, but anti-nationalism, rejecting the presidency of Israel.
Yeah, he was complex. He supported establishing a homeland for Jewish people, especially after the horrors of the Holocaust, hence his support for Zionism. But he was deeply suspicious of nationalism in general, fearing it led to conflict and oppression.
Which is why he turned down the offer to be Israel's president.
Exactly. He felt he wasn't cut out for politics and worried about the nationalistic aspects. He was also a pacifist initially, opposing World War I. But the rise of Nazism forced him to reconsider, realizing some threats might need to be confronted forcefully.
A pragmatic shift.
A pragmatic, albeit reluctant shift.
Yeah.
After WWEI, he became a huge advocate for world government, believing it was the only way to prevent nuclear war and control atomic weapons. He saw nationalism as a major danger in the atomic age.
He was also very outspoken about civil rights in the U.S., wasn't he? Especially racism against African Americans.
Extremely outspoken. It's a side many people don't know. He saw racism firsthand when he moved to Princeton. He called it a disease of white people in a speech at Lincoln University, a historically black university.
Wow. That was incredibly bold for the 1940s.
Absolutely. He saw it as a fundamental betrayal of American ideals. He also stood up for academic freedom during the McCarthy era, defending colleagues accused of communist ties, urging them not to cooperate with the witch hunts. He used his fame and moral authority to fight injustice.
He really practiced what he preached. Now, the image everyone knows. The hair, the casual clothes, the twinkle in his eye. What was he like personally?
Eccentric, definitely. But also warm, witty, approachable. He had his personal complexities, of course. His first marriage to Mileva Maric was intellectually stimulating, but ultimately strained. They had two sons, Hans Albert and Edward, and possibly a daughter, Liesl, who disappeared from the record,
And his second marriage.
to his cousin, Elsa Lowenthal. That seemed much more supportive and stable personally. She managed the household and protected him from unwanted attention. He also loved music. Playing the violin Mozart and Bach especially was a huge passion and escape for him.
Helped him think.
Apparently so. And he had that wonderful sense of humor, that ability to explain complex things with simple analogies, like the relativity one.
The hot stove and the nice girl.
Exactly. When you sit with a nice girl for 2 hours, it seems like 2 minutes. When you sit on a hot stove for 2 minutes, it seems like 2 hours. That's relativity. Perfect Einstein, making the profound relatable.
He really had a gift for communication. Which brings us to his writing, not just the dense scientific papers, but books for regular people, too.
Right. He wanted people to understand these revolutionary ideas. His book, Relativity, the Special and General Theory, from 1916, is a masterpiece of popular science. He explained it conceptually, philosophically, without heavy math. A classic.
And The World as I See It?
That's a collection of essays, more about his broader views on life, politics, peace, humanity. Shows his humanist side, his ethical core. Really rounds out the picture of the man.
Then The Evolution of Physics with Leopold-Infeld.
Yeah, that one plays modern physics in historical context, showing how ideas developed over time. All these writings aim to share the wonder, to make science accessible, to spark that curiosity he valued so much. He was a great educator.
So pulling it all together, his legacy is just immense, isn't it? Science, technology, philosophy, culture. He's everywhere.
Absolutely everywhere. Scientifically, he opened the door to the two main pillars of modern physics: relativity and quantum theory. Shaped everything from particle physics to cosmology. He didn't just contribute, he fundamentally changed the game.
And the technological fallout, not just abstract stuff.
No way. Photoelectric effect leads to lasers, solar cells, digital sensors. General relativity is essential for GPS, understanding gravity for space exploration. His theories have concrete, practical applications that shape our world daily.
Plus, he became the icon of genius, right?
The ultimate cultural icon. The hair, the name, it's shorthand for brilliance, creativity, scientific curiosity. He's the archetypal scientist in popular culture, instantly recognizable.
And that ethical dimension, considering the consequences.
That's a crucial part of his legacy, too. His anguish over the bomb, his advocacy for peace and scientific responsibility. It forced a conversation that scientists must have. What are the implications of our work? That discussion is more relevant than ever today.
And ultimately, maybe the biggest legacy is just inspiring curiosity.
I think so. That quote, "Curiosity is more important than knowledge." That captures his spirit. It's an invitation to everyone to keep asking questions, to keep exploring, to find wonder in the universe. Don't just accept, try to understand.
So his final years, he moved to the U.S., Princeton in '33, fleeing Nazi Germany.
Right. Spent his last couple decades at the Institute for Advanced Study there, working on the unified field theory, advocating for peace. He passed away in Princeton in 1955. Wished for cremation, ashes scattered secretly, disliked being idolized.
Though his brain was studied, famously and controversially.
Yes, that's a whole other story, taken without clear permission. Raises ethical questions. But his ideas, they live on powerfully. They're constantly being tested, confirmed, built upon.
Like the gravitational waves detection in 2015?
Exactly. LIGO detecting those ripples in spacetime, a direct prediction of general relativity from a century earlier. A stunning confirmation, opening a whole new way to observe the cosmos, shows how alive his theories still are.
So as we wrap up this deep dive, it's clear Einstein wasn't just a scientist. He was this profound thinker, a humanist, who reshaped how we see the universe and our place in it. He made the universe feel knowable.
And maybe that's the best final thought to leave everyone with. One of his most profound insights. The most incomprehensible thing about the universe is that it is comprehensible.
Wow. Let that sink in.
Yeah, it's an invitation, really, to embrace that curiosity, keep questioning, keep exploring. Find the connections like he did, from a simple compass to the deepest cosmic mysteries. Keep diving,